All right, the rest of this, let's look at the theory. It says to get a better approximation of the area under the curve, the area is divided into more and more rectangles. Yes, people did this once upon a time. For example, if we divide the area into 16 rectangles, we get L sub 16. So this case, instead of 4, you divide it into 16. So your subinterval would be 5 minus 1 divided by 16, and you're going to see that your rectangles are 0.25. So you get these little tiny rectangles here. And they've drawn, I took this from the book, they've drawn the left and the right. So you got the underestimate and the overestimate. And they calculated this for you. They did L16 and they got 13.59. We're going to believe them. And R sub 16 was 15.09. So we know that we have a better approximation using 16 subdivisions or 16 rectangles. Before we had it between like 11.5 and 17.5. Now it's better. We're getting closer to the true area. As a matter of fact, as the number of rectangles approach infinity, so we have infinitely many rectangles, the limit of the what we call Riemann sum becomes the area under the curve. All right, so that is the idea. And all of this summation ended up being an S here. And here's the definite integral. Let f be a continuous function on closed AB. The limit of the Riemann sums for f on closed AB is called the definite integral of f from a to b and is denoted, it's written the integral from, and you read the bottom one, a to b of f of x dx. A is the lower limit and b is the upper limit of integration. And this is the fundamental theorem of, well, not yet. This is just the development of the antiderivative of f of x dx from a to b ends up being that area under the curve. And then we'll put it together with antiderivative in the next section. So one more, I'll be back.